Good afternoon, everybody. My name is Steve Sapsford, and I am the chair of the Powertrain Systems and Fuels Group at the IMechE, and I'd like to welcome you to today's webinar, Improving Your Products Through Lifecycle Assessment. LCA is the best way to understand the environmental impacts of a product or service because it covers the entire product life cycle and examines multiple different impacts. This avoids the risk of burden shifting, by which well-intended interventions can cause unexpected issues elsewhere in the life cycle. As an example, the current pressure to shift to pure EVs on the basis that they are zero emissions ignores the emissions from the raw material extraction, the manufacturing processes, and the disposal and recycling associated with the full life cycle of the vehicle. So how do we take these impacts into account and make a fair comparison? Well, we need a sound evidence-based framework on which to base our key policies and decisions. So hopefully this webinar will explain how to deliver a robust LCA study, including how to avoid common pitfalls and select the appropriate software platform. And we will conclude with some recent case studies of Ricardo LCA projects. Now, don't forget to ask your questions as we go using the Ask a Question area just under the slides, and don't forget to click on the Submit button. If you are having any technical problems, though, please select the red Test Your Connection button, which will put you through to live support. In the meantime, I'd just like to introduce then Simon Gandy and Sam Hinton from Ricardo Energy and Environment, who've kindly agreed to present this webinar. I won't provide any more further introduction than that because they will do so as part of their presentation. So let's go.
Hello everybody, thanks for joining us today. At Ricardo, we're receiving more and more inquiries from businesses seeking to understand the environmental impacts of their products. Some are responding to regulations, some are seeking to gain a green market advantage. Many are simply responding because their customers are demanding action or data. Few of them realise that they'll also discover opportunities to reduce their cost. Therefore, whatever your drivers may be, it's important that you understand a bit about life cycle assessment and what it can do for you. In our webinar today, we're going to talk you through some principles of life cycle thinking and explain how life cycle assessment works. We'll talk a little about comparing LCAs and the possible software and data sources you might need to use. And then towards the end, we've got a couple of case studies and then we'll bring conclusions before taking questions from you. So we will start off with introductions. My name is Simon Gandy. I'm a chemical engineer by original training. When I left university, I spent about 7 years working for Procter & Gamble as a process scientist making shampoo. I then decided I wanted to change my career and spent a year at Imperial College in London studying for an MSc in environmental technology. Since then, I've been an environmental consultant, so nearly 20 years now, working first for ERM, then Navigant, and since 2010, my current company, AEA Technology, which is now Ricardo. My expertise, I would say, is primarily in life cycle assessment, but I do a wide range of additional work in subjects such as packaging and waste management. I do work on resource efficiency, and I also specialise in model design and quality assurance work. More recently, my work has moved into areas concerning the circular economy as well. But if we just stick to LCA studies, you can see here the sort of range of products and projects I've worked on: toilets, bricks, fertilizers. I've done all sorts of things, so there's quite a broad history of LCA work that I've covered over the past 20 years. Sam?
Thanks, Simon. Hi everyone, I'm Sam Hinton. I'm a senior consultant at Ricardo, specialising in life cycle assessment, and in particular using the SimmerPro software. I haven't been working quite as long as Simon, but I also have experience working on a wide range of LCAs, such as comparing whiskey byproduct use as a cattle feed or renewable energy, different road freight powertrains, recyclable fossil plastics versus compostable bioplastics. LCA is looking at passenger aircraft, comparing ammonia use as tractor fuel, combined heat and power, or fertilizer, and life cycle assessments of trains, just to name a few.
Sam and I work for Ricardo Energy and Environment. We are an internationally renowned consultancy that can trace its origins back to the 1970s, when our predecessors produced the first UK atmospheric emissions inventory and when the National Chemical Emergency Centre was established. We still specialise in providing scientifically sound advice to governments and businesses who are trying to tackle the diverse environmental challenges that face them. We have offices across the UK, our largest being at the Harwell Science Park in Oxfordshire. We're part of the wider Ricardo PLC, a global multi-industry consultancy for engineering, technology, product innovation and strategy, which employs nearly 3,000 staff in over 20 offices worldwide. Ricardo Energy and Environment offers a full suite of environmental services, as shown here. We employ industry-acknowledged experts and thought leaders in all these fields, meaning that we can support projects at many different levels, whether that be on a relative environmental risks and benefits of battery electric vehicles, or developing an overarching sustainability policy for a car manufacturer. For our part, Sam and I cannot profess to be experts in car components, or shampoos, bricks, or whiskey byproducts, but what we can provide is expertise and insight into the environmental credentials of these products using life cycle assessment. So, let's go on to some life cycle thinking. The first time I became aware of environmental issues was in the 1980s, when the UK was described by Scandinavian countries as the dirty old man of Europe because of its polluting coal power stations sending plumes of acid rain over into Scandinavian forests. This led to legislation controlling emissions from these power stations, by which time the focus was changing to the newly discovered hole over the ozone layer. And what I think might still be the most successful piece of environmental legislation in my lifetime so far, the Montreal Protocol was signed, banning the use of many of the ozone-depleting chemicals that were causing this ozone hole. Since the 1990s, climate change and global warming has dominated the environmental agenda, and it's still the most prominent issue, though we are seeing increasing discussions currently on other factors. So one example is local air quality, particularly in cities. 2 years ago, The Guardian reported that almost 40 million people in the UK live in areas with illegal levels of air pollution. That's 59% of the population. Naturally, given this history in my lifetime, it makes sense to look ahead to what might be coming next. In my opinion, the next environmental hot potato, if we can call it that, may well be resource security. This graphic from the European Environment Agency shows the percentages of global production of some critical raw materials that lie under the control of a single country. If any of your products or raw materials are listed on the graph, I'd be interested to know whether you've considered what might happen if the country in question decides it wants the materials for itself and stops exporting them. Personally, I can't imagine countries going to war over climate change, but I think things might be different when it comes to resource security. In conclusion, developments over my lifetime suggest that limiting your environmental considerations to carbon, which is the current environmental hot potato, seems likely to be short-term and perhaps short-sighted approach, and you really need to have a view over many different environmental considerations. Second thing I wanted to talk about was thinking about the whole life cycle. This plot from the former sustainability manager at Procter & Gamble shows total company energy consumption up the x-axis as a function of a life cycle stage along the left-hand side and product category on the right-hand side. He's been unsuccessfully trying to persuade management to switch their focus in efforts to reduce company energy consumption. They've been focused on company manufacturing energy consumption, which is the second item on the left-hand axis there. But then when he showed them the data from this study, the board went, aha, now we understand what you're trying to tell us. The completely dominating energy consumption for all of our products is nothing to do with our manufacturing. It's all about the use in the home of our laundry products. It was people washing their clothes that was the biggest energy impact associated with Procter & Gamble's products. Once the board understood this, they commissioned work to investigate low temperature washing powders, and that research led to new products which kept Procter & Gamble ahead of its competition for many years to come. What Procter & Gamble found, that the bulk of their environmental impact occurs during a life cycle stage that's not under their direct control, is typical. When Levi's looked at the impacts of their jeans on climate change, eutrophication, land occupation and water consumption, they found that the processes under their control were relatively insignificant. The big impacts arise during growing the cotton and caring for the jeans. More broadly, McKinsey's found that for a range of industries, more than 80% of a product's carbon burdens arise earlier in the supply chain. In general then, if you only look at the impacts under your direct control, you may be missing huge opportunities somewhere in the bigger picture. So far, we've only considered environmental impacts, but there's strong reason to extend the life cycle study to consider financial implications. The method is the same, determining the costs at each stage throughout the life cycle, rather than simply focusing on the costs under your control. Equipped with data on the complete life cycle costs, a product developer can choose the most cost-effective design overall. For durable products, expected to be made once but used many times, it's unsurprising that minimizing the use phase costs is key, which once again supports P&G's move to low temperature detergents. We've also seen life cycle cost arguments used to justify the higher retail price of energy efficient bulbs such as LEDs. Finally, a developing area of life cycle assessment is now looking to tackle the question of social impacts. There have been some high-profile media storms for certain companies, I can think of Topshop and Primark recently, who've been accused of using child labour. A social LCA study may look at some or all of these 5 key stakeholder groups: workers, local community, consumers, actors up and down the value chain, or just simply the whole of society, to explore what impacts they may incur as a result of products. The impacts assessed range from questions of employment numbers and levels through to child and slave labour, noise and health impacts, or various questions of inequality. In a recent exploratory social study we performed for a major global chemicals company, we identified potentially discriminatory concerns around incineration emissions and questions about the use of conflict minerals. I hope that's given you some context for life cycle thinking and why we think it's important. I'm going to hand over to Sam now to talk about how we do life cycle assessment.
So ISO 14040 defines life cycle assessment to be the compilation and evaluation of the inputs, outputs, and potential environmental impacts of a product system throughout its life cycle. This means we look at the impacts of processes within our control. For instance, if we are the manufacturer, the emissions associated with our factory. But we also look upstream to the impacts associated with producing the components we use. The impacts associated with extracting raw materials, impacts associated with distribution, perhaps retail, the use phase, and finally, end of life. And when we look at these impacts over the lifetime of our product or service, we can see that the hotspots may not occur within our direct control. And potentially, we need to design a more efficient product rather than drive efficient manufacturing, as Simon described earlier with his detergent example. So today, we're mostly going to talk about using lifecycle assessment to analyze contributions towards global warming. But please note that the ISO definition states environmental impacts, and this is not just carbon. And we can use this approach to look at a range of indicators. Some of those indicators, such as energy consumption, may show hotspots in very similar places to carbon emissions. But other indicators, such as ecotoxicity, can show hotspots in very different life cycles. So ISO 14040 also establishes a 4-stage process for undertaking life cycle assessments. The first step being goal and scope definition, and it's here we specify the question we're trying to answer. What is the boundary of the system that we're going to investigate? What's the functional unit of our study? Are we going to use primary data or secondary data? And what are the environmental criteria that we're going to assess our product or service against? So the second step is the lifecycle inventory. This accounts for the actual flows, for example, materials, emissions, energy and waste that occur within the system boundary. In effect, it is a mass and energy balance. So there might be 100 kilograms of aluminium components in the car engine, for instance. The third step is the impact assessment. This characterizes the inventory results into the final results to make them meaningful to the audience. For example, an aluminium car has a global warming potential of about 10 kilograms CO2 equivalents per kilogram. So the use of 100 kilograms of aluminium in the car engine might lead to a global warming impact of about 1 ton CO2 equivalents. The life cycle assessment is able to answer these questions, although the accuracy of its results do vary depending on the indicator that we're looking at. Finally, step 4 is interpretation. This covers analysing the results and drawing conclusions. Here we use techniques such as contribution and sensitivity analysis to dig deeper into the findings. And lifecycle assessment is an iterative process. This is why you can see arrows going in both directions between each phase. Once one phase is completed, it may be necessary to refine a previous phase, for example, the model assumptions. If you think back to the graphic I showed at the beginning, covering the different life cycles, where a hypothetical study showed a large ecotoxicity impact at end of life, in the interpretation phase, we would want to look at this closer and understand precisely what is driving the impact. Is this right? Do we need to revisit the inventory or even our system boundary? And lifecycle assessment may be directly applied for a number of purposes, such as benchmarking, product development, and strategic planning. Once we've got our results, the next step that many people want to take is to compare their life cycle assessment. We need to be quite careful when we compare life cycle assessments. Let's imagine we are looking at car bodies and whether to make them from steel or aluminium. The ISO standards for life cycle assessment are very flexible about the system boundary and other parameters that define a study. This can make comparing life cycle assessments of different products difficult or even impossible. In 2016, World Auto Steel and Aluminium Insider both published life cycle assessment studies looking at this question. Helpfully for World Auto Steel, it found that the lower use phase emissions of aluminium could not outweigh its higher production burden. It concluded, for all cases studied, the efficient steel designs show a consistent pattern of lower emissions in production, use, and end of life, which results in lower total cycle emissions. The aluminium designs showed high production phase emissions due to the energy-intensive manufacturing process, which is offset neither by the reduced use of emissions nor the significantly lower end of life due to the larger recycling credit. However, Aluminium Insider found the exact opposite, stating aluminium did have a lower life cycle impact. It concluded a car made out of a high content of aluminium instead of steel will generate a larger impact on the environment through energy consumption and greenhouse gas emissions during its raw material and production phases, but it will have a much lower impact during its product use phase, and most important of all, a lower impact in its whole life cycle assessment. On this basis, it can be stated that as far as life cycle assessment indicates, aluminium should continue to replace steel. Now, to combat this difficulty in comparing life cycle assessments, environmental product declarations, which is a specific type of life cycle assessment, follow instructions called product category rules in order to enable comparison. Environmental product declarations are public reports that should enable customers to compare products and select the more environmentally friendly option. On screen you can see an environmental product declaration that we prepared for James Jones on their timber I-joist. James Jones wanted an EPD of their product because it enables their customers to score extra points in building certification schemes such as BREEAM and LEED. So I've talked a bit about the importance of selecting an appropriate system boundary, and the example from World Auto Steel and Aluminium Insider illustrates the importance of comparing like with like, but it is also important to compare systems over a range of indicators. So if we consider electricity generation, conventional wisdom suggests that solar PV is preferable to coal. And for global warming potential, this is certainly true. Over its lifetime, solar emits 8% of the greenhouse gas emissions that coal does. But global warming potential isn't the only environmental issue. Per kilowatt hour, solar requires substantially more infrastructure. And if we look at indicators such as abiotic resource depletion, we see that coal is preferable, consuming just 3% of the minerals used in solar PV. And perhaps surprisingly, when we look at ozone layer depletion, coal is also preferable, emitting 48% as many CFCs over its lifetime. Now, it's important to say that the amount of minerals depleted and CFCs released is several magnitudes less than carbon emissions in these two examples, which, without going into the complexities of weighting environmental indicators, suggests that we should care more about the carbon emissions. But this is a good example of how we might shift harm from one environmental issue to another. If we consider electric vehicles, we can see a double burden shift, where we move the burden from the use phase to electricity production and from air quality to issues such as resource depletion and ecotoxicity. Now I'm going to hand over to Simon, who's going to talk through some software and data sources.
Thanks, Sam. People have been doing life cycle assessment since at least the 1970s and possibly before. With the advent of modern computer techniques and big data, it will probably come as no surprise to you that many potential platforms exist for practitioners to perform LCAs. There's a wide range of proprietary tools, many of which are founded on the EcoInvent database, which contains peer-reviewed inventories of thousands of previous LCA studies performed around the world. Packages such as SimmerPro from Prey and Gabby from ThinkStep are full LCA tools that both contain EcoInvent data and facilitate highly detailed studies. The Waste and Resources Assessment tool for the environment, RATE, was developed for the UK Environment Agency for the specific analysis of household waste management, and is typical of a range of sector-specific platforms. At Ricardo, our clients frequently want a bespoke LCA tool that they can use themselves for subsequent investigations. We tend to build these tools in Microsoft Excel using a subset of the EcoInvent database and customize the user interface to facilitate sensitivity analysis and scenario tests of interest to the client. And I'll show you a couple of examples in a moment. But if we just think about the data collection and imagine we're talking about a typical manufacturer here, an LCA study needs data on the types and quantities of raw materials going into the product, information about all the utilities used, water, electricity, fuels, data about the wastes and emissions arising from the production process, and of course the outputs from the production process. Not many processes produce electricity, heat or steam, but in several projects we've had to tackle the question of byproducts and how to allocate impacts across more than one output. There are established means for doing this, however, so it's not been tricky, but it is an extra consideration sometimes. All of this information we gather largely from the client, supplemented where necessary from literature, in order to construct the life cycle inventory. In order to perform the life cycle impact assessment, the last data set we need is all the relevant emission factors for the inventory items, and that's the data that we typically get from EcoInvent or one of the proprietary software tools. An alternative data collection method uses the EcoChange software. This Dutch company has been operating since 2011, and its clients include our own Ricardo Performance Products team and Shuren. The significant advantage of the EcoChange software is that its output is in an LCA for every product made at a manufacturing site, rather than the tradition which you may just manage to do one or two products at a time. Do what EcoChange call activity-based footprinting. The study begins by mapping the total emissions from the company. This is a list of the likely data sets required to complete that high-level assessment. It includes things like data on the energy consumption, direct extractions, and you also need to know the suppliers and where they're located. In order to drill down from site level to product level, the next stage is to allocate the collected information to individual production processes on the site. So having found out the total energy consumption, we then need to know the energy consumption for the individual processes, similarly with the emissions. Finally, the use of those processes has to be allocated to the different products manufactured. So how much of that process's time is used to produce each of the products? And for that we need information on things like the bills and materials for the products being made. And that's it. 3 data collection and manipulation steps, and we're ready to start viewing and interpreting the results. I put everything on one slide here so you can see the entire data requirements. I guess it may look a bit daunting, but I don't think it's too demanding if we look at these things in detail. The things that I've ticked here, I believe most companies already collect and record. So these data should be available once you can try and track them down. Furthermore, most companies also have this remaining information to hand as a result of their various existing reporting requirements, although it might be a bit harder to find. If you believe that, and this has been our experience, such a process actually becomes more of a data collation exercise. And once you've got all of that information together, it can be used for other things such as supporting corporate reporting for the various requirements that are necessary these days. But as I mentioned earlier, the other benefit is that we can produce an LCA for every product made at the site and potentially an EPD as well. I told you I'd show you a couple of slides of what an LCA tool might look like, This first screenshot is the user interface from the LCA tool we built for the Science and Technology Facilities Council, looking at using ammonia to store stranded renewable energy on a remote farm, and then using that ammonia for heat and power, for tractor fuel, or for fertilizer. On the left-hand side, the user can adjust some key parameters, such as the size of the wind turbine or the crop and soil type being fertilized. On the right, the tool presents its results in tables and graphs. So we've got an opportunity here to change some of the key input parameters and immediately see how they change on the outputs. We've done many rate LCA assessments, mostly for local authorities and the waste management companies that work for them. A typical rate model starts with a pile of waste and seeks to optimise the bins, lorries and treatment methods to maximise the environmental benefits of the waste management service. This model was a relatively simple one. However, it's also possible to model complex systems, and this shows the full model of one local authority's waste collection services. Finally, this is a shot of LCA and risk management tool called GRACE that we built for the Green Investment Group. This requires just a few items of data input, as can be seen on the left-hand image. The tool uses background databases from Econvent to estimate the associated environmental impacts. On the right-hand image, there are results for global warming, fossil fuel consumption, and emissions of NOx, SOx, and particulates. The tool also rates the possible risk that these environmental results might not be achieved. Okay, I mentioned that we thought it'd be helpful to present a few case studies on how we've used LCA in practice to help our clients. In 2017, we performed a lifecycle assessment of the production of a supercar engine at Ricardo Performance Products in Shoreham. Ricardo provided us with utilities data covering water and energy consumption and production, and waste production data. Bill of materials information was extracted from the International Material Data System, IMDS, which also revealed the supplier locations. So the data collection was not at all onerous for Ricardo. We loaded the data into the EcoChain software, which analysed the flows against 25 different environmental indicators, including acidification, ozone depletion, and resource consumption. Looking at the hotspots of the results that were generated, and here we're looking at contribution towards global warming, we found that more than 25% of the carbon footprint of the engine arises from the cylinder block alone. Another 25% arises from the cylinder heads, piston assemblies, and turbocharger. The next 4 components contribute a further 10%, and all the rest of the 100 or more components together contribute a third of the carbon footprint. Notably, only 3.5% of the global warming potential actually arises from Ricardo's operations at Shoreham, and transport impacts account for even less. Waste management is also here, but its contribution is even smaller. We've been able to report to the manufacturer, to the car manufacturer, that Ricardo's operations make a negligible contribution to the overall carbon footprint of the engine. Accordingly, the focus is now on Ricardo's suppliers earlier in the supply chain. The results can be cut in different ways. This plot shows how different raw materials contribute to the engine's global warming potential. We see that over half the impact arises from just one material, aluminium. This reflects the high carbon footprint associated with the manufacture of aluminium, which is a very energy-intensive process. As mentioned earlier, we can examine 25 different environmental indicators using the data from this study. This plot looks at resource depletion. Once again, about 50% of the impact arises from aluminium. We can compare this analysis with the earlier graph from the European Environment Agency on critical materials. Encouragingly for Ricardo and its client, only two materials, chromium and magnesium, appear on that list. So they can be relatively comfortable that they don't have too much to worry about in terms of material supplies. Okay, pass over to Sam now to look at our second case study.
Thanks, Simon. So this second case study is an example of using lifecycle assessment to support design selection. So a European public transport provider wanted to understand the global warming potential of exchanging steel components within its trains for aluminium and composite components. So working with partners in Ricardo Rail, we created 3 lifecycle inventories for the client's train to calculate the carbon impact of swapping steel components for lighter alternatives. So these inventories represented a low-weight train with composites and aluminium, the default materials, and a high-weight train with more steel components. We built scenarios into the model to represent different operating options, such as regional and intercity uses. And we added waste scenarios to assess the impact of poor and high recyclability of the different materials. Grid options were added to compare the current and projected grid mixes, as well as a 100% renewable scenario. And the outcome of these different scenarios was given in tons of CO2 equivalents. The model also assessed the amount of primary energy consumed. So this chart shows the results, the carbon impact of lightweighting the train. The blue bars represent procuring the raw materials. The orange bars illustrate the impacts of manufacturing an item. The yellow is the assembly of the train. And there is also a green section which reports negative numbers, because sending materials to recycling avoids the production of virgin materials and the systems get a credit. So looking at the net results, we can see that while the steel train is the heaviest, there is a carbon cost to lightweighting, and the steel train has the smallest carbon footprint associated with its manufacture and disposal. However, when we compare these capital burdens to the operational impacts, we can see that the capital burdens are relatively insignificant. Comparing the operational impacts, we see that lightweighting delivers global warming potential benefits that far outweigh the relatively higher capital burdens. We also assessed how this picture changed through grid decarbonisation, and the issue then becomes how much energy you expend at each point. In effect, you save money. You save more money by operating more efficient, potentially more expensive to build rolling stock. So as mentioned at the start, we have performed life cycle assessment on a very wide range of products, and this study supports a general rule of thumb, which is that for energy using products, the best life cycle outcomes tend to arise from minimizing energy use during the operational phase. So to conclude, Lifecycle assessment is a scientific assessment of the impacts of a product over its entire life cycle. It considers many different environmental indicators that can also examine financial and social implications. It enables us to go after the real hotspots in our product, which may occur outside of our direct control. If we think back to those burdens occurring in the use phase rather than in our hypothetical factory. And while lifecycle assessment is a very powerful method, we do need to be careful when using lifecycle assessment for comparative purposes. This means following clear guidance, such as product category rules, to ensure that we're making fair comparisons. It's also important to consider the platforms. There's many lifecycle assessment platforms out there which lend themselves to different tasks, and you need to select the best one accordingly. And finally, one general rule of thumb when looking at different energy using scenarios is to go after the more efficient processes rather than focus on resource use impacts. Thank you very much.
Sorry, I think I was on mute there. So I was just going to go through the questions then, please. Thank you, Simon and Sam, for that presentation. Most informative. I just wanted to start with one from the top that we'd already thought of before the start of this, Simon and Sam, which is from the LCA studies you have done. Can you recommend where a manufacturer should start looking for their biggest environmental impacts? And perhaps we could link in Barry Piakowski's question about whether there are any grants or incentives to repatriate products rather than shipping them from elsewhere if the environmental impact is better.
Thanks, Steve. Yeah, sure. Okay. So are there any, I guess we can say that all the studies we've done are different and they all tend to produce different results, but we do have some rules of thumb. As we said in the earlier slides, we've found that generally the biggest impacts occur outside the factory gate of the manufacturer. So they need to be looking up and down their supply chain to make sure they've got the whole picture. So that's the first thing. With any products that use energy, as Sam just mentioned, it tends to be the use phase that's the most significant and the energy consumption. So whatever you can do to minimise energy consumption during use is very important. And then the third thing, transport. We rarely find transport is particularly important. So things like people talk about food miles, worry about where their food is coming from. The shipment of food is often very efficiently done, and the bigger impacts occur in growing the food or maybe cooking it. So generally transport is not such a big impact. So if we look at Barry's question, which was talking about whether there are any grants or incentives to repatriate manufacturing, so generally I'd say shipping stuff from the Far East is not a significant impact compared with things elsewhere in the supply chain. But to answer the direct question, I'm not aware of any grants or incentives that might exist to encourage that behaviour.
Okay. Alexis Rees asked a question about how do you you mentioned in the presentation about looking at different indicators or metrics that you're trying to do the life cycle analysis of, and the question is how do you compare the different environmental indicators, decide which is the most material or impactful?
Yeah, that's a really good question. There isn't a right answer to that. It will depend on a company's own priorities. So I'll get Sam to say something in a minute about the product environmental footprint, but we're doing work for companies at the moment and looking at a wide range of indicators, and they've asked that very question: should we be worrying more about global warming or acidification? And the only way you can address that question is to look at the relative impacts. And if you're comparing two products, look at the impacts of those two products against each one and try and come up with an idea of which is the more significant difference. So one might be larger than the other, but if the scales of magnitude are very different, maybe it's easier to say which one's better. But there isn't, I mean, people write PhDs on this sort of thing. Do you want to say something about the PEFs now?
Yeah, I will. I'd just add to what you were saying there, Simon, that so what we tend to use when we carry out these life cycle assessments are midpoint methods, where we look at the emission of a substance, and then from that we can determine what the global warming potential is, or the acidification potential, or what we're looking at. And as Simon said, that's quite hard to compare whether an emission of CO2 is better or worse than the emission of some acidification. But there are endpoint methods as well that take these midpoint emissions and then from that look at what harm is that causing. Now that introduces a great deal of uncertainty, but it does make it potentially easier for people to understand the context of the stuff we're looking at. Now, the PEF initiative that Simon was mentioning, this is a European initiative, and what is special about that is that in their PEF category rules, they set representative products, so that when you undertake your assessment in accordance with their rules, you benchmark your product against an average wine or an average beer or an average battery, and that is quite a departure from other LCA that we see.
Okay, thanks for that. Stephen Crossley has asked whether, in your view, are the rates of LCA use increasing or decreasing over the last 5 years or so? Are people getting more interested in doing it as they kind of realise the full impact, or what would you say?
I'd have to say that my experience is that it's becoming more prevalent. The work that I do in our company, I do quite a wide range of modelling. I do waste flow modelling, I do life cycle assessment traditionally, but the amount of time I've had to do other modelling over the past few years has diminished significantly, and I'm now pretty much doing life cycle assessment full time. And the number of people in our company is growing. We've got 5 or 6 practitioners who are doing quite regular projects now. So yeah, I think there's definitely increasing interest in people trying to get to the bottom of their environmental impacts. Okay,
thank you for that. I think lots of people have noticed that there are these things are great frameworks, but you are in danger regarding the assumptions that you make and things like that. John Gallagher has asked about accounting for the operational energy or CO2 emissions during the operational life cycle, and effectively you're basing that on projections, and there will be uncertainty around that. So for that train example, is there a way of including some uncertainty in that analysis so you get a spread that says on the whole it'll be better, or there are certain situations where it wouldn't be?
Well, certainly we find, as we've mentioned, that when energy use is a part of a product or a system that we're modelling, it becomes really important. We did an LCA recently for a company who had a very novel technology that was looking at turning some accepted processes upside down, but it uses a lot of electricity. And we found that if we used the UK grid mix for 2016, it wasn't best for the environment. And if we used the UK grid mix for 2018, it was. So we found it was highly sensitive to the grid mix. So yes, what we tend to do is try and make sure that where electricity becomes important, we've got a good idea of how we think electricity is going to progress in the future. And certainly we do a lot of uncertainty analysis around those predictions to understand how fragile our conclusions are or how robust they are, depending on what happens in the future.
Excellent. So I think that actually covers Stephen Roach's question as well, which is about how do you future-proof some of this. So that's terrific.
Yes, it's all about... my preferred way of doing an LCA is to try and get to the first answer as quickly as possible. So we'll sometimes make assumptions on the way through and we're not quite sure whether they're right or not. But if we assume on the pessimistic side of things, and when we get to the end, it turns out not to be important, then we can be comfortable that factor is not important. Conversely, if it turns out to be quite important, then we go around and do a second iteration of sensitivity to understand in more detail how uncertainties within that parameter can affect the overall results.
Yeah, okay, understood. So Simon and Sam, really, a question here about, so can we use LCAs then to inform governmental or local authorities or cities with regard to policy decisions?
Yes, I think a good example of that is a project that we did for climate exchange up in Scotland, where they wanted an LCA to help inform their biopolicy recommendations. So they were interested to understand what was the best thing to do with some byproducts from the whiskey industry, namely using that for animal feed or using it to produce renewable energy. So we built a model for them that accounted for a range of different scenarios, such as what energy was being displaced at whiskey distilleries, different transport scenarios, and we looked at using the feedstock to produce simple animal feed or combine it into a highly nutritious feed or to use it for renewable energy generation. And the results of that study fed into CXC's biopolicy recommendations to Scottish Government.
Okay, thanks, Sam. Another question from Barry Piakowski here regarding, we spoke about raw materials cross-referencing because of risks of supply shortage and their impacts on the economy. So does the software also perform the same comparisons with real-time IMechE candidate list data for REACH compliance? I don't know what any of that means, but I hope you guys do.
Well, I can imagine we have colleagues who know this in great detail, but I confess I don't know what the IMechE is either. The software does have quite a detailed toxicology. It looks at human toxicity and marine toxicity and things like that, but I don't think it directly cross-references REACH compliance.
Okay.
I don't think it would be difficult to extend the study to take those sort of things into account, but I don't think we'd be able to do it in our software platform.
Okay, thanks for that, Simon. And here's the question I've been saving for the end, because we're almost out. There's a couple of others here. Let me just have a quick look. Yeah, have you ever done an LCA that came out with a result that the client didn't want, and what happened? Kind of came out with the wrong answer, guys. What are you doing?
Yes, we have done that. So for me, when we do an LCA, we're not trying to stack the results and give the client what they want or the answer they're hoping for. We're trying to give them an honest assessment of their environmental impact so that they can make the right decisions. And this was another project where we were comparing quite different alternative uses of a particular product. And we found that for climate change, their preferred solution was somewhat better than everything else, but they suspected that was already going to be the case. And what they really wanted to know was how their alternative fared for all of the other indicators. And we looked at about 10 or 12, I think. And what we found was that for most of the others, the current process was actually better. So at the end of the study, they said to us, well, thank you very much. That's been a very informative study. It's told us exactly what we wanted to know. We are in a much better position now. We're going to put that report in our desk here, and we're not going to look at it again. And we'd rather you didn't ever tell anybody about that. Thank you very much. And that was all the work that we did for them. So we gave them a very clear answer, but it wasn't what they wanted, and so they said, okay, you're not to tell anyone about that. So this is why I can only be very vague about what the project was.
Excellent. All right. Thanks for that. Well, we've just got a couple of minutes left, so I was going to finish with this question here from Peter McBrien, which is going to be good fun. So, okay, after all of that, does an electric vehicle win over a comparative conventional petrol vehicle, I guess, or hybrid or whatever? Who wants to have a crack at that?
I think the simple answer to that is it depends. It's the classic LCA answer. We can imagine scenarios where if your grid mix is highly dependent on coal, it's not going to win out, or it's going to be a very close run thing. Whereas if we were to run it on more modern grid mixes, or if we were to run it somewhere that's particularly low carbon like France, I think it's going to win quite significantly.
Yes, I mean, Sam's right. There's an awful lot of different parameters going in here, but as we're talking about an energy using product, it's all about its energy, really. We're doing a major study for the European Commission at the moment on lifecycle assessment of vehicles, and we're looking at electric vehicles in quite a lot of different guises. We're looking at petrol and gas and hydrogen and diesel.
And renewable low carbon fuels and things?
And biofuels and all that sort of stuff, that's
synthetic
right.
Fuels, yeah.
Yeah, it's something like a 2-year study, and we're about halfway through it, so I'm afraid we don't have the answer yet. But the idea is that we'll help the European Commission in the future to set policy that isn't just based on, oh, we think everyone should be driving electric vehicles, but actually takes into account the whole life cycle, particularly the energy, or the way that energy is generated for electric vehicles, but also thinking about the resource depletion of the solar cells that you might need and things like that, so that we're giving them a total environmental answer.
Yeah, and the energy involved in the manufacture of the battery packs and all that kind of stuff.
And the rare materials that it uses. If we all have electric vehicles in the future, there might not be enough cobalt in the world, or indium, I think, is another rare chemical. So it's all of those things as well.
Okay.
That's a big question. I'm afraid there isn't a simple answer.
No, but it was a bit of sport at the end. So
I would still like to have a hybrid. I think that's probably the way I'd go.
All right. Well, we're in up to the end of the time slot. So please just let me thank Simon Gandy and Sam Hinton from Ricardo Energy and Environment for a fascinating presentation, and thanks to all the contributors with their questions and things like that. The slide material will be available on the resources section of this. I don't know how to do that, but I'm sure that will all become apparent later on. So I'd like to draw this session to a close, and thank you all very much.
Thanks very much. Bye-bye.
Thank you.
Bye-bye.